Okay, Assalamualaikum and good morning.
Alaikum salam. Good morning again.
Alaikum salam, Doctor.
Now we continue our lecture about the boundary layer. So there are three main parameters that you should know about boundary layers, which is boundary layer thickness, and then we will go for displacement boundary layer thickness and also momentum thickness of boundary layer. So this is the basic one. I think you already know the definition and so on and so forth. So we go first the boundary layer thickness. So it is written as delta like this one. So the delta here is the boundary layer thickness, and actually if we have a boundary like this one, okay, at the boundary layer of this like this one, and the boundary layer thickness is actually the physical thickness, means you could measure the thickness of the boundary layer at this point, and at this trailing edge, for example, the boundary layer is from here to here. Okay, so because boundary layer thickness can be measured from the experimental. So if you could capture the boundary layer image, so you could measure it directly. Okay, and boundary layer thickness is actually exists. So it is a real thing. Okay, so the basic idea, if you have a layer, the boundary layer like this one, so you just measure from here to here. So but the problem is we need to measure from the surface here until what condition we want to measure it here. So we make previous researcher, so they make a stand that boundary layer thickness delta is a distance from the surface where the local velocity equal from the surface to a location where the local velocity equal 99% of the free stream velocity. So you need to stick with the idea of 99%. So means that if we have a velocity distribution here, so let's say this is our velocity distribution. So we need to know where is the 99%, where the u, the local velocity that has 0.99 capital U, mean 99% from the free stream velocity. So let's say we have a velocity distribution here. So because we have a no-slip condition, the velocity is 0, and then the velocity is start to increase slowly. So might be this is 10%, 20%, 30%, and finally we will get 99% here. So and then this molecule might be 100%. So 100% means it is equal to the capital U, the free stream velocity. So mean the boundary layer thickness is actually the distance from this molecule, 99%, to the surface, to means to the molecule of 0%. So this is the boundary layer thickness delta. So and then same, so means that if you want to draw a boundary layer, so we need to draw a line, a path, mean a locus actually, or we need to connect the point of every 99% of U of this one. So means that it start with 0, and then we connect with all the point that has 99% of free stream velocity. So this is the borderline. So the borderline between the velocity that has velocity distribution and the region that only has a constant velocity here. Okay, so means that first you need to understand that boundary layer thickness is the physical thickness. So we could measure the thickness of that layer. So it measured vertically. So mean it's measured on y-axis. So this is the y-axis. Okay, this is the y-axis. So we measure on y-axis vertical. So from the surface where the local velocity means the small u, where the local velocity is 0 until the place, the location where the local velocity here is only 99% of the free stream velocity. So this is the boundary layer thickness. So, and then boundary layer thickness is occur depends on at what coordinate you want to measure. So means that if you want to measure at the trailing edge here, the last point of the plate, so this is the delta for x1, for example, because might be this is the location of x1. So if you want to measure it here, so you could measure it by mentioning this is that delta x2, for example. So, and then because the location here is x2, so means that on every location, so you could measure the boundary layer thickness. Okay. Then that is the definition of boundary layer thickness. Then we need to express it into the mathematical expression. So we could write just this one. So we have the delta, and delta is actually the distance on y-axis. So the delta is the value on y-axis from, for sure, from 0 until the local velocity is 99% from the free stream velocity. So mean this is the mathematical expression for the boundary layer thickness. Okay, so the legend is here. So we have delta is the boundary layer thickness, y is distance in y direction. So u, small u is local velocity. Local velocity means velocity for one molecule here. Okay, so and the capital U is the free stream velocity. Okay, because, so this is the very important parameter. We need to estimate the boundary layer thickness, but the mathematical expression here is very simple. It's very straightforward. So mean delta is equal to y. So it's nothing can we do. We can do any calculation or what that, because the equation is very simple. Then we need to estimate the delta by use the idea of shear stress. But before we do that, okay, we must make sure that our equation, fulfill the continuity equation and also the momentum equation. Okay, to fulfill of all of that, okay, we introduce you the displacement thickness of boundary layer. So it shown as delta and star here, delta and S3. Okay, certain we always call it as delta star. Okay, so delta star here will show you the displacement thickness. Okay, this displacement thickness is actually the imaginary thickness. So it cannot be measured. It cannot be measured whether you could take pictures of boundary layers or not. Boundary displacement thickness is actually not exist in the real world. It's just an imaginary distance, imaginary thickness to fulfill the conservation of mass. So the distance again, so it is actually the distance of the surface would have to move in y direction. So mean we need to move a little bit the distance in y direction in the vertical axis, okay, to reduce the flow passing by a volume equivalent to the real effect of the boundary layer. It is because to make sure that our calculation can reflect the real situation. Okay, or in simple word, they could say that the displacement thickness is actually to make sure that our calculation is fulfill the idea of conservation of mass. Okay, this is the basic idea of delta star. So how to do this? Okay, so please imagine something like this. So let's say we have a flat plate here. So and then the velocity from before it touch the flat plate will have a constant velocity. So like this one. So we have a constant velocity here and it's labeled as capital U. So and then when it's travel on the flat plate here. So you know the shear stress create the no slip condition and so on. And then we will have the velocity distribution like this one. Okay, this is our velocity distribution. So and then we assume that the delta here is the thickness from the zero here. So until where the location is equal to u. Okay, so this is, later on I will explain again. So here at this stage, you just take that, because the first definition is u equal 99% of capital U. That is the borderline of a boundary layer. So to simplify our calculation, we just assume that we take location where the local velocity u equal to the free stream velocity. We just round the number of 99%. So we take the border where the u is equal to capital U. So I will explain it later at the end of this slide. Okay, so because it will create two types of solution. Okay, so at this one, okay, to simplify this calculation, so we take the condition as u equal to capital U. So means that the delta here is the distance from the u here, from u equal to 0 to u equal to capital U. So this is the velocity which has capital U, which is the means that this velocity is actually same with this free stream velocity. Okay. So and if we see this diagram, we found that if we count all the molecule here, so this molecule is actually more compared to the molecule at this area, because this area is quite, it's a curve here, so it's remain an empty space of this one. So mean the balance, the mass is not the same. So this will ruin our calculation. So to make sure that our mass is constant, so what we do is we take all the mass at this area, and then we create another area of this one. Means that the rectangular area, we transfer all this area. So we transfer all the molecule in this area to make sure that our mass will be constant. So we put into this area. So this area already has a constant velocity. So means the total of this, what we have on this green area, is actually we put in this area. So then it could create a delta star. So means that we just imagine that. Okay, we transfer the area from here into this area, and we need to determine what is the height that can be created. So that is the meaning of the displacement thickness. So from here we found that, okay, we need to increase the thickness of this one. Mean we need to create another thickness here, which is delta star. So this is the meaning of the distance the surface would have to move in the y direction. So this is the distance that you should move in your diagram to make sure that the volume, means the mass, the volume, equivalent to the real effect of the boundary layer. Okay, the idea is, in simple word, is to make sure that the conservation of mass is being fulfilled. Okay. Okay, now we could start an equation here, okay, by the idea of conservation of mass. So we know that density is mass over volume. Then to calculate the mass is rho times volume. So so we have mass here, and we have density here, and we could calculate the volume. So the volume here is length times weight time height time width. So we could assume that the length is actually capital U here. Okay, the height is the delta. So, and then the width here, we just assume that the width is equal to 1 unity. So it's time by 1. So we could say that the mass for this term, for this area, it can be written as rho U n delta. Okay, so and then based on this diagram, I think you already know that the conservation of mass, the equation for conservation of mass can be written as mass for A must be equal to mass for B plus mass for C. So that's what we have here. And mass for A is rho U delta, and mass for C it can be easily found. It is equal to rho U n delta. So if we have this, the area is only the rectangular shape, so we could calculate it as rho U n delta star. So that's what we have here. So the problem is how to calculate the mass for the for area B. So I think you already know this idea. Because the area is not symmetry, okay, it's increased like this one. So we start our calculation on calculating the mass for the small area. So for the small area, so mean the mass for the small area, the M here, is equal to, it carries the same equation. So we have rho, and then the U is small u, and the delta here means the height here, okay, is actually the dy. So, and then when we want to calculate all the area here, so I think you already know, we integrate both sides here, so we'll get the mass for B. Now it's equal with the integration of rho u and dy. So that's what we have here. The rho u and dy is the value of mass for area B. So the integration needs limit. So we put our limit is delta n 0 because we are do our integration with dy. So we have the delta here and we have 0 according to our diagram. So if you solve this problem, so you could do this, I think you could understand this term. So we bring the delta star to the left because we want to find what is delta star, and then we do some reverse calculation. We just put integration for rho u delta, and then we could merge the terms into this one. Okay, so and then we bring the rho u here to the right hand side, so we have this one, and finally we could say that delta star is actually this term. So this is the equation for delta star. So finally, I hope you could remember the delta star here is equal to 0 integration 0 to delta 1 minus u over u dy. So please bear in mind that this small u is the local velocity, and this small this capital U is the free stream velocity. So in my handwriting, I will write u minus u over capital U like this, with u with a bar here to differentiate my between small and capital U. Okay, then I would like to introduce you another imaginary thickness. We call it as momentum thickness. So in the simple words, previously in delta star, we make sure that our calculation will fulfill the conservation of mass, and now in momentum thickness, we want to make sure that our calculation will fulfill the conservation of momentum. Okay, so again, it carries the same ideas. It's actually the surface that we need to move in y direction, okay, to give same total momentum as exists between the surface and the reference plane in a real fluid. So the idea is to make sure that what we calculate, the momentum that we calculate in our theory, will reflect the same momentum that occurs at the real world, at the real situation, or in the others, in other words, it's just to make sure that the conservation of momentum being fulfilled. Okay. So the idea is the same. Okay, we just bring the momentum that occur at this area, the loss area here, into this part. So I think you now understand. We have the rectangular shape with the length of u. So means that we just need to calculate what is the thickness of this delta. So and then the momentum can be calculated by the idea of mass time volume at mass time velocity. So to make it easy, so I make table like this. So for inlet, so this is an inlet, the A. So we have rho u and delta, the mass. So and then for outlet, for B here, so we discussed it previously. So it is integral of rho u dy. So for C here, so we have rho u delta star, and for this one, for D, it's become rho u and theta, because the height here, our new imaginary height is equal to theta. And then the velocity, the output velocity here, the input is u, capital U. The velocity for B, okay, the velocity for B area is small u, and the the velocity for C and D is the capital U. Okay, so that's what we have here. So and then we write momentum for inlet must be equal to momentum for outlet. So we have one inlet and we have three outlet here. So this is the momentum for D, and this is momentum for C, and this is the total momentum for B. So and then so in this stage, we have problems because we want to carry out what is the equation for theta, because we are now analyzing the momentum thickness. However, in our terms here, we have delta star, which is the displacement thickness. So what we could do is we replace the value of delta star here with the of this for this equation. So this is the equation that we found previously. So we substitute in the equation, and then we bring theta to the left hand side to become our subject here. So and then we could simplify the theta into this equation. So finally, I hope you could remember the equation of theta here is integration of 0 to delta u over u1 minus u over u dy, which is the u is the local velocity, capital U is the free stream velocity, theta is the momentum thickness. Okay, so this is the very basic equation for this one. So in that example, very straightforward. So for example, we have u over u here, which is equal to y over delta. And then we need to determine what is delta star over delta and theta over delta. So if you want to find what is delta star over delta, maybe we could start with the equation for delta star here. So we substitute the value of u over u with y over delta. And then we could get it is equal to 1 over 2 delta. So finally, we could say that delta star over delta is equal 1 over 2. And also for the momentum thickness here, theta. So this is the equation. We substitute the u over u here with y over delta. We do the integral. We substitute the limit 0 to delta. And finally, we could get theta over delta is equal 1 over 6. So this is very important because in boundary layer, a lot of equation will have the theta function. Delta star is okay. It's not quite not so familiar, not appear in many equations, but theta will be appear in many equations. So make sure that you could calculate the value of momentum thickness.
Doctor,
Yes.
is this condition standardized for every situation? Meaning that delta will be equals to will always equals to 1 over 2 delta?
Okay. For this situation, for y over delta, yes, it will equal to 1 over 2.
So it's not applicable to every situation,
Right.
right?
So it's depend on your velocity distribution.
Okay.
Okay, so you need to, every time when you get velocity distribution, then you need to start with this equation. Okay, can you get me?
Yeah.
Okay. So, and then I would like to share with you what is the meaning of U over U here. Okay, so, and this is actually the relationship with the previous topic. So in previous topic, so we are focusing on development of U. So the development of velocity. So we have a lot of situations. Sometimes we get uy, sometimes we get ur, and then u theta, and so on and so forth. So means the idea of for chapter 1 to 3 is actually to develop your understanding on how to get the velocity distribution in so many applications. Why? Because boundary layers is not only occur at aerofoil. It can be occur inside a pipe, whether your pipe is circular shape or rectangular shape. So it all also occurs when your application is only about 2 plates, for example, in co-ed flow. So the boundary layer can occur on that situation too. And then to calculate boundary layers, to calculate the effect of viscosity in terms of drag force or lift force. In certain application, you will have lift force, but normally, for example, if flow in pipe, we only have drag force. And the drag force of flow in pipe is actually reflected into the ideas of major loss in flow in pipe. So there is actually the different name, but it starts from this same phenomenon, which is the effect of viscosity, the resistance that occur when your fluid has viscosity. So for sure, your fluid has viscosity. Okay. So the idea from the chapter 1 to 3 is actually to get the velocity profile. I think you already know. So from the velocity profile, you could imagine the formation of your boundary layer. So and then, but in boundary layers top chapter, we usually use the idea of U over U. Okay, why? Because our main equation, so if you see the equation for delta star and theta, it is written in U over U. So it is good for us if we could show our velocity distribution in terms of U over U equal blah, blah, blah. So I think if you look back your previous notes in chapter 1 to 3, so whether it is just two parallel plate and so on and so forth, so you will get the velocity of u is equal y 2 over h over y and so on and so forth, something like this. So this and then might be you have 2u here and so on and so forth. So this is you bring the capital U here to the left hand side to have u over u like this one. So another idea about u over u is, okay, so it is actually the ratio. So for example, you have the velocity profile like this one. Okay, so u is actually the local velocity of this one. And then let's say the maximum velocity here is the capital U, the free stream velocity. So the U over U here is actually reflect the percentage between local velocity here with the free stream velocity at the top. Okay, so means at 0 here, so the U is 0, so means that the thickness is 0. So and then the percentage U over U here at certain percentage and so on and so forth. So I hope you could imagine the physical meaning of U over U being presented in this chapter. Okay, so that's about the basic equation that will be used again and again in this chapter. And then here I would like to propose to you the idea of von Karman equation. Okay, so what is a von Karman equation? Okay, if you refresh back the idea of boundary layer, we are actually aim to get lift force and the drag force. And then we cannot calculate that force because we have difficulties to find the value of shear stress. And until now, the equation that I propose to you is do not contain any tau terms. So means that there is still no hope for you to get shear stress from those equations because there is no tau. And now in von Karman equation, I will introduce you the idea of von Karman to rearrange the idea of viscosity effect and to propose their von Karman equation of shear stress. Okay. So the idea of von Karman is actually same with the previous idea. So let's say we have an inlet here. So because it's not make any contact with on surface, so means the velocity here is constant. So we name it as a capital U, means the free stream velocity. And after it move on certain plates, so the velocity has no slip condition, and then the velocity distribution is like this. So why this happened? This happened because there is the deficit of momentum. There is losses in momentum. So because this molecule is being forced to stop, so mean the momentum is losses now. So and then von Karman tried von Karman use the area of this one to calculate the amount of the losses momentum. So and then of the loss momentum. So the momentum equation is mass times velocity, and mass can be calculated by the idea of rho times volume, and volume can be calculated by this area times width. Okay. So let's say we enlarge that area, so we have this one. So because this area is not symmetrical or not easy, not a common shape, so we start to calculate with a small area like of this one. So let's say we have a very long thin strip, so we assume that the thickness is dy, and then we assume that the length of this green strip is capital U minus U because the local velocity is U, and the total, the average, the free stream velocity is capital U here. So we could assume that the length of that area is U, capital U minus U. So and then mass for this green area can be written as this one. So mass times rho and volume. So we have rho here, and volume is the length of the strip, U minus U, and B is the width, and dy is the height. Okay, so this is the width, means you just imagine that the strip is something like this one. Okay, so this is U minus U, capital U minus U, and this is B, the labor, okay, the B, and this is the thickness. Okay, this is the dy. Okay. So and then the means that the deficit of momentum, okay, we just give a small d, for example, is m times v, and m is rho U minus U B dy. And then the U here, okay, please be careful about this U. So this U is not U, capital U minus U. This U is actually the momentum, the velocity of that molecule on that level. So on this level, so we found that the molecule is moved with small u velocity. So we use the small u here as the velocity. Okay, please be careful about that, because normally student will take capital U minus U because, okay. So, and then this is the equation to calculate the momentum deficit for this small strip. So this small area.
Doctor, sorry, I missed you. Why you need to multiply a U in the deficit again?
So because the equation for momentum is mass times V, mass time velocity.
Oh, okay.
What you have here is actually the mass only.
Oh, okay.
Okay, so it means you need to multiply with V to get the momentum. Okay. So and then you know that to get the total momentum that we need to integrate it. So we integrate the limit is from 0 to this is 0 and it's 0 to delta, because you know when the local velocity here reach or equal to u equal capital U, so the thickness here is actually delta. So means that I think you have idea here to get the total momentum. So we need to integrate the deficit momentum for the small area. So we integrate the small d here. So this is just my writing style. So I just assume that momentum deficit for a small area is small d, and then when we integrate the small d, it will become the capital D. So that's the way I show the small area and the total area. So this is not actually the real mathematics law. So please ignore it. Okay, because in certain textbook they will use different different symbol. So I just use D. Okay, and then we get the total momentum deficit here D, and then because the integral is 2 dy, so we bring out all the constant value. So we have the rho and B here. So and then we could to simplify this calculation, okay, we times with u square over u square. So that's why we have a u square here and we have a 2u here. So this is u square, and this u times with this u will give you another u square. Okay, why? Because this is actually to simplify our calculation later on. Okay, so why we need this? Because it can give us this kind of equation. So if you get this kind of equation, you could say that this term is actually equal to the theta. So now the total momentum deficit proposed by von Karman is actually rho b u square and theta. So then to simplify our calculation later on, we differentiate this term into dx. So we have d dx is equal rho b u square d theta dx. Okay. Okay, so this is the first equation proposed by the von Karman. Okay, next. So the momentum losses, okay, so I mean the deficit of momentum is actually caused by a friction. Because there is a friction, then the momentum will reduce. So we could say that the momentum losses, dd here, is because of friction, and that friction can be calculated by tau times dA. So dA means the total area. So we have tau here, and it times with b and dx. So what it means? Okay, let's say we have a very long plate like this one, and then we just focus on one small area here. So let's say the area is 3D now. So means that this is the total x, the x-axis, and this is the dx. So I think you could imagine this one. So and then the width is a constant b. Okay, so and then okay, so we have this one. So the a here is b times dx. So that's why we use b times dx, and then we bring the dx here, okay, to the left hand side. So we have dd over dx equal to tau b. Now you could see that we have ddx here and ddx here. So next what we could do is we equalize equation 3 and 2 and 3. So we have ddx equal rho b u square d theta dx equal tau and b. So and then we could simplify it, become tau equal rho u square d theta dx. So this is known as shear stress of von Karman equation, or sometimes we call it as von Karman equation. Okay, so this is the first equation that you know, that you should remember. So and then next, again, before that, Newton's also proposed a viscosity law. So Newton says that viscosity also, viscosity or the shear stress can be written as mu du dy. And here, please bear in mind that you need to put a condition, which is y is equal to 0. Why we need to put y equal to 0? Because the maximum shear stress is actually occur at y equal to 0. Because it is totally different, the shear stress when the liquid or when the fluid molecule stick on a surface. Because it stick very hard, then it will create the velocity is equal to 0 compared to the intermolecule strength. So it is between two fluid molecule or two gas molecule. So it is relatively weak compared to what happen of molecules staying on a solid surface. Okay, that's why we need to put the condition of y equal to 0. Okay, so means that here we have equation of delta, but the equation of delta is quite straightforward. So and then we have equation of delta star and theta, and then I propose to you the idea of tau from the Von-Karman, and also just to remind you the equation of tau from the Newton. Now I think you could see that the equation of tau is come out, and then we need to merge everything. We need to use the velocity profile that we have, then we need to get our tau, and then we need to get our drag force and lift force, and as well as the coefficient of drag and coefficient of lift.